Hello and welcome all to this session of Heat Power Engineering. So today we will start a new module, that is a module number 3, and it is called as the air cycles. So we will start with an introduction to air cycles, or basically what do we mean by a cycle in case of thermodynamics. So we'll first understand what do we mean by thermodynamic cycles, then we'll go on analyzing the concepts of thermodynamic cycles, the various interactions or the various parameters that are associated with a certain thermodynamic cycle, and then we will move on to the discussions of reversible process so that we can identify a reversible cycle from an irreversible one. Okay, and then we shall discuss the concept of efficiency. So we will discuss a general concept by which we can explain the efficiency of a thermodynamic cycle. So let us start our discussions. So to start with thermodynamic cycles, we must understand what a thermodynamic process is. We have already discussed these things, so this will be a little recap so that we can understand the concept of thermodynamic cycles easily. Okay, so what we will do, we will try to understand what a thermodynamic process is. Now, any thermodynamic process is a change. It defines a certain change from a specific state to another state. And what do we mean by state? Say water is boiling at 100 degrees Celsius. That means this temperature, this 100 degree Celsius temperature, gives you an understanding that this water is really hot, and at this temperature water will be converted into steam. So this is what we call as a thermodynamic state. So there are some thermodynamic parameters like temperature, pressure, volume, and there are some other parameters also. I will not get into that presently. So if we understand these parameters like pressure, volume and temperature, then we can always define the change of any system in terms of this pressure and volume. So if we draw a diagram where we will define a certain state, that means suppose this is a point in this PV diagram. So obviously it means that this has a certain pressure, and corresponding to this pressure it will obviously have a certain volume. So when we know these two pressure and volume, we know that the system is existing in a certain state. Now let us consider that system is now receiving some amount of heat or work from outside. There is some energy interaction or there is some mass flow going on. So that means the system will change its characteristics. So that means which was initially at P1 V1, it will move on to a different state. That means the pressure and the volume of the system has now changed. So it is changed from P1 V1 to P2 V2. Now what is happening here? This pressure is getting reduced and the volume is getting increased. Okay, so corresponding to this, you can see this is the final pressure, and this is your final volume. Okay, so this was actually the initial volume, and now you can see that this was actually V1, and now this is your V2, that means the final volume. So the volume has changed from V1 to V2. Okay, that means there is an expansion, there is a thermodynamic expansion going on. So now if we try to understand this change of states, then what will happen? We can draw a curve like this. Okay, we can draw a curve like this so that it indicates the change of state from 1 to state 2. So this indicates a thermodynamic process has been carried out. And now if exactly the opposite process is carried out, that means if there is again some amount of compression to the system, so that the system goes back to its initial condition like this, then what is happening here, what we can observe here, we can see this red line, it indicates a closed loop or a closed figure. That means if this is our initial state 1 and if this is our initial state 2, then we can say that the system was initially at state 1. That means the system initially had a pressure of P1 and a volume of P1, and after the process has been carried out, after the two specific process that has been carried out, an expansion followed by a compression, we can see that the system has reached its initial condition. That means it has completed a thermodynamic cycle. So thermodynamic cycle means the initial condition and the final condition of the system should be as uh, as earlier it was. Okay, so the initial conditions and the final conditions would be exactly as it was earlier. Okay, so it will be equal always. The state parameters will be equal. Okay, the pressure which was initially P1, you can see from this diagram, it got reduced to P2, but after the compression has been carried out, it got increased to P1. So this is what the thermodynamic cycle is. So thermodynamic cycle means the the initial conditions and the final conditions would be exactly same. There will be no change in the initial uh, and the final conditions. Okay, so as you can see over here, a thermodynamic cycle will have the same and exact initial and final conditions. Okay, so now let us see how the different parameters uh, in terms of heat transfer, work transfer, and internal energy, they go on changing with respect to the thermodynamic cycle. What is the effect of heat transfer or work transfer or the change of internal energy for these thermodynamic cycles? So let us check that. So in case of any thermodynamic cycles, a basic thermodynamic relation is always maintained. And what it is? In case of thermodynamic cycles, all the heat transfers, that means here you can see that there are two specific processes, so you can always create a various loop. Okay, so that, let us consider this is a cycle. Okay, so this is your first process, then this is your second one, then this is your third one, then this is the fourth one, and going on like this. Here it ends here, so that the final state and the initial state, they are exactly equal. Now for this process, for this cycle, if you see that there are various kinds of heat transfer and work transfers involved in all the processes. Okay, then what will happen, how do you find the relationship between heat and work transfer for thermodynamic cycles? It will be very simple to understand. The sum of all heat transfers, the sum of all heat transfers. So if we write dq as the heat transfer, then sum of all heat transfer, the summation signs means if there are say 5 processes, then all the heat transfers that has been done in all of these 5 processes, they needs to be add up, and then we can move on with the calculation. So that means we can say that the sum of all heat transfers for a thermodynamic cycle would be equal to the sum of all work transfers involved in all the processes for this thermodynamic cycle. Okay, it is very easy to understand. Okay, is that clear? So sum of all heat transfers would be equal to sum of all work transfers in a thermodynamic cycle. Okay, so the sum of all heat transfers, just a minute, I am writing down. um, sum of all heat transfers will be equal to the sum of all work transfers sum of all heat transfers will be equal to the sum of all work transfers for a just a minute, I spelled all wrong over there. Sum of all heat transfers will be equal to the sum of all work transfers in a thermodynamic cycle. Okay, so this relationship should be always remembered, because this will be always followed when we discuss the basic air cycles. That means, being an automobile engineer, you have to deal with the automobiles, that means with the engines, and for most of the engines, like say petrol engine or diesel engine, there you will find that air is the most important component over there. So for that case, you need to understand the characteristics of this thermodynamic cycle. You need to understand that the sum of all heat transfers that are involved in this thermodynamic cycle, they will be equal to the sum of all work transfers. And coming to the second point, regarding the change of internal energy, how would you calculate the internal energy change for a thermodynamic cycle? How you can do that? Now that is the question. So you will find, as discussed earlier, you know that internal energy is nothing but a state point. Okay, it depends on the state function. So let us consider the internal energy at the state 1 was E1. Then after the expansion process that has been carried out, it got changed to E2. So if you are interested to find out the total change of internal energy, then how we can do that? So you can write du, you can simply write du for process 1 to 2. That means you are calculating the change of internal energy for the process 1 to 2. Then what will be the change? Change always means final minus initial. So E2 is the final internal energy. E2 is the final internal energy, whereas E1 is the initial. So simply it would be E2 minus E1. So E2 minus E1. Okay. Now coming to the next part, next process over here. So you will see the internal energy has changed from E2 to E1. For the process 2 to 1, you will find the internal energy has changed from E2 to E1. Then you can simply write du 2 to 1 is equal to here final minus initial. So E2 was the initial case, and then it got changed into E1. So this was your initial internal energy, then it got changed to this E1 because of the compression. So now if you try to find out the total change of energy, internal energy for this thermodynamic cycle, what will happen? You can simply write du 1 to 2 plus du 2 to 1. That is very simple to understand. Then it would be what? It would be E2 minus E1. It would be E2 minus E1 plus E1 minus E2. That is as simple as it is. Now tell me, what will be the change in internal energy? It is very simple to understand. Then you will see that this E2, they will be getting reduced from the equation, and ultimately we will find the internal energy change, which is denoted by du, or sometimes you will find that it is also denoted by dE also. So for a thermodynamic cycle, the change of internal energy will be always 0. So this is the second most important point which a student should always remember. So an automobile engineer should always remember this. The sum of all heat transfers will be equal to the sum of all work transfers in a thermodynamic cycle. And coming to the second part, the sum of the internal energy change, the internal energy change for any thermodynamic cycle would be 0. Okay, so let me write down this fact so that you would be able to remember this. Okay, so the internal energy change for any thermodynamic cycle would be thermodynamic cycle would be always 0. Okay, so that is the point. So first of all, we came to know that sum of all heat transfers will be equal to the sum of all work transfers in a thermodynamic cycle, and secondly, the internal energy change for any thermodynamic cycle would be always 0. So these two are the basic thermodynamic relations. They are involved in any thermodynamic cycles. So when we will be discussing the Carnot cycle, the Brayton cycle, the Otto, diesel or dual cycle, we will find that this relationship is always applied, and this relationship is always found to be true for any cycle. Okay, that is absolutely true. Okay, so you should always remember this. Then coming to the next part, where we will discuss what do we mean by a reversible cycle or reversible process. Then we'll be able to understand what is a reversible cycle. So let us move on to that. So just now we have discussed that any thermodynamic cycle means that the initial states and the final states of the system would be exactly same. Now, coming to the definition of a reversible process or an irreversible process. Now, from basic understanding of the words reversible and irreversible, we can understand that a process which can be reversed in both the directions, they can be called as irreversible process. So this is a definition. This is not a specific definition. Okay, so this is a general understanding. It doesn't mean that when a process can be reversed in both the ways, it is not irreversible process. So it doesn't necessarily mean that a process which is which is which can be reversed in both the ways is a reversible process. We'll see that why it is not so. So generally, the different thermodynamic processes can be characterized into two specific ways. The processes which can be carried in only one single direction, and the other one is the processes which can be carried out in both the directions. Okay, like let us consider a vehicle is moving in the road. Suddenly someone comes in front of the vehicle and you apply your brake. So what will happen? There will be a certain amount of frictional interaction between the tires and the road that will generate some thermal energy. Okay, so what is happening? Vehicle was moving, you applied the brake, frictional heating or frictional thermal energy generation happens. But so this is a process. Okay, that means the kinetic energy of the vehicle is being transformed into frictional heating. Okay, now if someone thinks that he will reverse this process, that means he will cool the road surface, and with this cooling he will try to generate the kinetic energy. That means by cooling the surface he will try to move the vehicle. That means that is impossible. That cannot be possible. So you cannot move the vehicle by cooling the road surface. So that means this is a process. This is an example where this process can be carried in one single direction only. Similarly, if we consider a process, uh, there is uh, there is some tea or water in your bottle, and you need to drink this water at a certain say 70 degrees Celsius. But since you have uh, made it uh, made it open in the air, its temperature got reduced. That means the temperature which was initially at 70 degrees Celsius, it got reduced to say 40 degrees Celsius. Then what happened? You again heat it up. You again boil it, or you just give some amount of heat transfer to it, so that its temperature can be increased to 70 degrees Celsius. So that means the water got cooled, and now you are heating the water. So that means a body, a system uh, can be made, there can be a change made for this system where the temperature may decrease, or you can again uh, increase the temperature of the system by increasing some amount of, or by doing some amount of heat transfer. Okay, so this is a process which can be carried out in both the ways. That means the cooling and the heating. So this can be carried out in both the ways. So among these two processes, you will find that no process is reversible. Okay, so you must understand one fact: no no natural process no natural process is reversible. Okay, no natural process is reversible. Or you can understand, you can say that all 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 natural processes are irreversible. Okay, so these are the same thing but written in two different formats. So no natural process is reversible, or you can say all natural processes are irreversible. That means you cannot find any natural process which would be reversible. So how we can find out irreversible process? So we have already discussed the concepts of reversible process while discussing second law of thermodynamics. So if now, before going to the discussions of reversible process, let us discuss what are the reasons that cause these irreversibilities, and what do we mean by these irreversibilities. So let us try to find that. Let us try to understand what do we exactly mean by the word irreversibilities. Okay, irreversibilities. So what do we mean by irreversibilities? So it is nothing but the resistance present within the system. Resistance present within the system. What kind of resistance we are talking about within the system? Suppose a ball is moving in a ground. The ball will not move for infinite time. It will obviously come to stop after some time. Why? Because there is frictional force. Now you know that the viscosity that exists when the fluid is flowing. Okay, so because of fluid viscosity, the fluid, after moving a certain uh, with a certain velocity, it gets uh, at a static position. It gets its velocity gets reduced. So there are some internal resistances always present within the system. So when electricity is flowing, you will find the concept resistance is always present over there. So in all natural systems, all systems where some amount of quantity is flowing, you will find that there is a quantity which is called as resistance, and which is always acting on the direction opposite to the direction of flow. So these resistances, they create these irreversibilities. Now these irreversibilities can be categorized into two uh, two processes. Okay, so the first one is the internal irreversibilities. Internal irreversibilities. Okay, the second one being the external irreversibilities. Irreversibilities. So the first one is the internal irreversibilities, and the second one is the external irreversibilities. Okay, so these are the two categories of irreversibilities. Now, what do you mean by internal irreversibilities? Just now we have discussed it. It means the internal resistance which is present within the system. So for a moving system, when a solid is moving over a solid surface, there will be friction, there will be fluid viscosity present within the fluid flowing system. You will find resistance in case of electricity flow. So these are the internal irreversibilities which are always present in the system. Now coming to the external irreversibilities. So whenever there is heat transfer, whenever there is work transfer, why these quantities are flowing? Heat only flows when there is a certain temperature difference. If there is no temperature difference, then heat will not flow. It is a quantity which we call as energy in transit. Work is exactly the same. So whenever you will find there is a difference in force, there is a difference in pressure, you can obtain work. So work is a quantity which also flows. So this heat, this work, these flowing quantities, they are the example of external irreversibilities. And since any process where you need to make an interaction happen, you will always understand that this external irreversibilities will be always present over there. So any natural process will be always irreversible. Okay. Now coming to the reversible process. Coming to the definition of reversible process. So from the definition of cycle, we have already understood that a process, a collection of process where the initial condition and the final condition for the system is exactly the same, we can call it as a thermodynamic cycle. Now, reversible process is something where both the system and the surroundings, they need to be brought back at the initial condition. So reversible process means both the system and the surroundings, they will come back. So both the system and the surroundings, they needs to be present at its initial condition. Now in general cases you will understand that the system can return back to its original position, but the surroundings will be always permanently disturbed. There will be permanent disturbance happened or caused when a certain process is being carried out. Now I can give you an example. Suppose in a class of 10 students, I take 100 rupees from a student. So let us consider that initially I didn't have any money. I took 100 rupees from a student, and then what I did, I distributed this 100 rupees among 10 other students. Now what is happening? I don't have any money still. So I have returned back to my initial condition. I had 0 rupees, then I took 100 rupees, and then I had distributed this 100 rupees. Now what is happened when I have distributed this 100 rupees? The thing is that the 10 other students have now 10 rupees each, and the student who had this 100 rupees, he has also this 10 rupees. So he has lost the 90 rupees, and the other students, they have also received 10 rupees. So there is a permanent change in the surroundings, whereas the system has returned back to its initial condition. So reversible process means both the system and the surroundings should be returned back uh, I'm sorry, for any reversible process, both the system and the surroundings should come back to its original initial position. Okay, that is the point I should discuss. Now coming to the concepts of cycle. So when all the processes involved in a thermodynamic cycle are reversible, then it should be called as a reversible cycle. So when all the processes, so just let me write it down. When all the processes involved in a thermodynamic cycle, in a thermo just a minute thermodynamic cycle are reversible, then then it can be called as a called then it can be called as a reversible cycle. So if any one process becomes irreversible, then it would be an irreversible cycle. So all the processes should be reversible. Okay, so reversible cycle. Okay, so when all the processes involved in a thermodynamic cycle, when all the processes involved in a thermodynamic cycle are reversible, then it can be called as a reversible cycle. So we will discuss the concepts of all reversible cycle in our syllabus over here. So I have already told you that we will discuss Otto, Diesel, Brayton, dual, and Carnot cycle. Carnot cycle is the first one which would be discussed. So all these cycles are conceived as a reversible cycle. That means all the processes are always considered to be reversible. Okay, but practically when these processes happen, in reality they are not reversible at all. Okay, all of them are irreversible. But to idealize the processes, to conceptually think about these thermodynamic processes, we think them as a reversible process so that we can find the maximum possible efficiency. So everything should be discussed from a frame of reference. Okay, the maximum efficiency is found from any reversible process. Okay, so this is why we think of this ideal reversible processes which would give us the maximum efficiency, and we can compare the efficiency of the real case corresponding to the ideal one. Okay, this is why we conceive or think of these reversible cycles. Okay, so the basic concept is that any process can be called as reversible if both the system and the surroundings they are uh, coming back to its initial position. Okay, and if all the processes involved in a thermodynamic cycle are is reversible, then it will be called as a reversible cycle. Okay, and if any one of them becomes irreversible, then it will be called as an irreversible cycle. Okay, now with this discussion, let us move on to the concept of efficiency. How do we define efficiency for any thermodynamic cycle? Okay, so let us see that. How can we define the efficiency of any thermodynamic cycle? Okay, so let us see. So let us consider a thermodynamic cycle where you can see Q1 is the heat addition, Q2 is the heat rejection, W1 is the work done by the system, and W2 is the work received by the system. So here you can see, that because of this input thermal energy, the system is doing some amount of work. It is generating or it is transferring W1 amount of work. But during the completion of this thermodynamic cycle, it is also consuming the work of W2. So what is the net work? If a system is transferring or generating the work W1 and it is the system is consuming W2 from this then the W net would be simply W1 minus W2, because W1 is the net work which is being produced and W2 is the work which is being consumed. And what is the heat input? So if you write heat input, then it is only the Q1, because of this heat input the system is able to transfer this work. Okay, so heat input would be simply equal to Q1. So any concept of efficiency would be discussed from this basic and fundamental point of view. Efficiency means what you are getting as input and from where you are getting this input, from where you are getting this output. So what you are getting as output is the basic thing, and what you are giving as input. Okay, so efficiency means, so we generally denote the efficiency by this sign. It is called as eta. So eta means the W net, that means the work which you are getting as net output, and the heat input. Okay, so let us consider this is your Q1. So here you will find the net work is W1 minus W2, and it is divided by Q1. Okay, now the question is, if you consider this thermodynamic cycle, then you must remember the sum of all heat transfers should be equal to the sum of all work transfers. So W net means it will be equal to Q net. So the sum of all heat transfers should be Q1 minus Q2. Why this minus? Because heat is being rejected, and when heat is being rejected from a system, it is always taken as negative. So Q1 minus Q2, this is your net heat transfer. That would be equal to the net work output. That would be W1 minus W2. So you can simply replace W1 minus W2 as Q1 minus Q2 divided by Q1. Okay, which you can also write as 1 minus Q2 by Q1. Ultimately you can write it as 1 minus heat rejected. So heat rejected, okay, divided by heat addition or heat input. Okay, so the heat which is being rejected divided by the heat which is being taken as the addition to the system. So you can define the efficiency in terms of this also. So there are two things by which you can define the efficiency. The primary or the fundamental law is this, W net by Q1. So this is the efficiency for any heat engine, mind it. Okay, so this is the definition of efficiency for any heat engine. Okay, and whereas this is the efficiency in terms of heat addition and heat rejection. So you should remember this. Okay, so this is how we can define the efficiency. Now, for since we will be dealing with all reversible cycles, it is easy to understand that there exists a certain relationship between heat transfers, that means the heat rejection and heat addition, with the temperature at which the heat addition and the heat rejection is taking place. That means what I am trying to make you understand is that there is a certain relationship between the heat transfers and the temperatures at which the heat transfer is taking place. So let us consider this is an isothermal heat addition. Here you can see this is happening at a constant temperature T1, and this heat rejection is happening at a constant temperature T2. Now, for reversible cycles only, always remember, for reversible cycles. So for reversible cycles or reversible processes, any one of them, these ratios of heat transfers, that means heat addition divided by heat rejection. So this is the ratios of heat transfers, that is equal to the temperature at which these heat transfers are taking place. So you can see that this heat Q1 was added at a constant temperature T1, that has been written over here, and this heat rejection also was also going on at a constant temperature T2. So this is a important relation. So that means the efficiency can also be expressed like this, T2 by T1. Okay, so T2 being the temperature of heat rejection, T1 being the temperature of heat addition. Now, there are some cycles where you will find this total heat is not added isothermally. That means temperature is changing when the heat addition is taking place. So you might not think of such processes where the temperature can remain same and the heat addition can take place. Yes, this is possible for reversible heat transfer. Reversible heat transfer means it will take infinite time to make the heat transfers with infinite small temperature differences. So when the heat transfer will take place, there will be infinite thermal energy reservoirs where the temperature difference will be very low, infinitely low, so that the heat transfer can take place in an way in a way where it would consume infinite time. So in that case, heat transfer can be done keeping the temperature constant. But in other cycles, you may find that the temperature of heat addition is going on changing. So in that case, this would not be a correct expression. The expressions would be changed depending on that nature. Okay. So this is only valid for Carnot cycle. So we'll be discussing the concept of Carnot cycle in the previous case. So the concept of efficiency is that output divided by input. What is the output here? The work is the output. The mechanical work is the output. What is the input here? The thermal energy is the input. The heat addition is the input. Okay. So output divided by input. And you can also express in this format. 1 minus heat rejection divided by heat addition. And for reversible processes or reversible cycles, this can be an expression too. Okay, so these are the concepts of efficiency. We will discuss in detail the concept of efficiency for each and individual cycles. So till then, goodbye and thank you. In the next class, we will start discussing about the concepts of Carnot cycle. Okay, so if you have any questions, you can mail me at arindam.mukherjee@dscc.ac.in. So till then, goodbye and thank you.